Hello class, this is CSE-5250, sections 2 and 60, week 10, spring 2026. I'm Giovanni Orijuela, and let's talk about the OpenMP benchmarking project really quick. So, the instructions are going to be more or less the same as that of the pthreads benchmarking project. It's just that in the past I had students benchmark a different program, but this time I want for you to try benchmarking the sorting algorithm that I gave you for assignment 3. It's going to be a little bit tougher because it's just going to take a lot longer to benchmark because, let's face it, we are doing this on the CPU and there is no way we can get close to that theoretical big O of n. So the next best thing you can do is just cut down the sorting time by some fraction proportional to however many threads we can run our program with. So, as before, chances are you've already done these instructions already, unless you're doing this on a different machine, but just double check to make sure your computer is up to the task. And then just take a mental note of how many CPU cores your system has, and by extension, how many threads your system can handle. So, once again, we are working with the odd-even transposition sort algorithm that we looked at in OpenMP assignment number 3. You're going to want to make a few slight modifications to it, even more than the ones that I have talked about. If you have the stopwatch, good. It's just that we need to make one more modification. In fact, if you have the stopwatch already, you're already ahead of the game. Okay, but what modifications do we need to do? Well, all our programming assignments thus far required us to pass in a thread count. We need to pass in an array size as well. So, chances are the start of your main function might look like this, with a thread count being parsed as the first command line argument, following the name of the executable, of course. You're going to want to modify it to look something like this, where you pass in an array size and then the thread count. And that's just to follow how we have been benchmarking our projects thus far. We lock into a specific work size and then change the thread count. Then we change the work size and then work our way up with the increasing thread counts from there. So yeah. I will also mention, if you know how to write a batch script or a shell script, and that if you know how to also write it in such a way that you can repeatedly run the same program over and over and over again, you'll be even more ahead of the game. One other modification I would also advise you also try out is this. If you wrote your program in C++, if you wrote your program in C++ and you have the stopwatch implemented using the chrono library, add in some extra code so that it writes the execution time to a file. And then you can do what I did when I took parallel programming the first time, and that was literally run the script, the batch script, so that it does all the benchmarks in one go. I would just leave my computer overnight running, doing its thing, and then once I have all the results, I would just take all the numbers, punch them into Microsoft Excel, and then do the necessary analysis that way. So if you know how to do any of that, then it is worth doing, because that way you will have automated the entire assignment with one script. But you still have to do the analysis as well. Anyway, as before, you're going to create a table not unlike this, but because of the nature of transposition sort, the array sizes aren't going to correspond to the sizes that we have worked on with the other algorithm that we have worked with, the pi estimating algorithm. We're starting with the size 1000 array. And this is an array of random numbers. We're gonna try each array size with 1, 2, 4, 8, and 16 threads. If your system has more processing power and you can go up to like 24 or 32 threads, good, go for it. Add an extra column or two. Get as much numbers as you can. If you cannot get it to run with a size 1 million array within a reasonable amount of time, don't worry about it. Instead, do something like this down here, where here I added intermediary sizes. So it is 1,000, and then it goes up to 3,000, and that is because if you put the numbers 1 through 10 on a log scale, the number 3 is going to be somewhere in the middle. So that's why it goes 1,000 and then 3,000 and then 10,000 and then 30,000. Either way, you're going to want to do these benchmarks. And as I said, if you cannot do 1 million in a reasonable amount of time, don't. And do something like this instead. Okay? Okay. I should mention that the main thing that we are timing is how long the sorting algorithm runs. We are not so much concerned with the runtime of the random number generator or the print statements. We're more concerned with the random number generator. No, not the random number generator. We are more concerned with the performance of the sorting algorithm itself. If you are unable to implement a stopwatch that times just the sorting algorithm's performance, just make a note of that in your report. Like, if it is such that you can only time, you're only able to time the performance of the whole program, like from start to finish, starting with the generation and then ending with the print. If that's all you can do, make a note of that. What we should see is performance based on how large the array is. So if you can just get the timings for just the algorithm, the more the better. But if you can only get the timings for the whole program, just make a note of what you timed in your report. Okay? Okay. Let's go back to the instructions real quick. You will also need to create a table of speedup. So much like before, for the entire table that you've made, for each array size, divide all the times by the corresponding one thread time, and then you'll see what your speedup is. Optionally, what you could do is, in Excel, you can import all these numbers into a table, and then create a graph that way. That's what I did. And honestly, it was way more fun, because you get some good visuals of what the performance looks like. Like, if you consider the one thread case that is taking 100% of the runtime, increasing the thread count should result in this exponential decay curve. I have a hard time trying to visualize it on my webcam, but it should be an exponential decay curve, more or less. And it is exponential because the thread count is going exponential. It's not a linear increase. It's an exponential increase, so exponential curve. But anyway, the whole point of parallel programming is to get our computers to do more work in less time, but only for specific work cases, and this is one of them. And as I said, we are likely poorly unequipped to get our sorting algorithm to that theoretical big O of n. The only other piece of hardware I can think of that could get to that level of performance is parallel programming on a GPU, or distributed programming. If you get the distributed programming, that's already within the realm of MPI. That's when you have a network that's where you have a network of computers working as though they were one computer. Parallel programming on a GPU, you can leverage even more cores than what you can on a typical CPU. But the same is true of distributed programming, except you have the bottleneck of how fast Okay, so if you are doing distributed computing, your bottleneck is how fast you can get signals from one computer to another computer. Because everything's connected over a network, and that's your next bottleneck. We are gonna get the MPI in the third part of the semester. Okay? And as before, you will be answering the following questions. Where do you think the sweet spot was for thread count? Where do you think the sweet spot was for workload size? At what point did you stop seeing any speed improvements? And at what point did you stop seeing at what point did you stop seeing speed improvements, and at what point do you start to see a worthwhile speed up for work size? There is a fifth question, and that is, how do you compare your experience with programming with OpenMP compared to pthreads? Was one harder than the other? And number 6 is an optional one. That is the question that has you expand the tables by adding an additional column for even larger thread counts. One thing I did not add in here, but could be worth doing, is adding a size 100 case and possibly a size 300 case. That is to get even more timings for even smaller work cases. But in doing this benchmark myself, I got timings that were way too small for millisecond precision to be good enough. So if you do decide to do that, you might want to swap out millisecond precision for microsecond precision. If you do that, in the code for the stopwatch, just swap out milliseconds for microseconds. And now you can time the whole program on microsecond precision. This is assuming you are using C++, and by extension, this is assuming you are using Chrono and by extension C++. All these extra libraries here will not work if you're using pure C code, but it will work if you're using C++ code. And one more thing, if you do use C++ for this, your GCC compiler, swap that out for the G++ compiler, assuming you are compiling this on a Unix machine. Okay, so that's gonna be it for the quick overview on what your project is. If you have any questions, definitely feel free to let me know. And oh yeah, the due date. Because we have spring break upcoming, I have set the due date for this assignment to be not the Friday of spring break. That would be really weird. Instead, it's set to April 10th, and it's set to close on the following Sunday. So it's due on the 10th, and just in case something comes up and you can't submit it on time, you have until the 12th to submit it on time. So that's it. That's going to be the whole project. If you have any questions, let me know. And when we come back from spring break, we are going to look at MPI. Okay?